Good morning to all of you. So today I am going to discuss the second unit. In the second unit, there is a second half that is steady flow energy equation. So the first law of thermodynamics can be classified as a flow work and non-flow work. So now it is connected to the flow work. So that some steady flow energy equation applied to the various realistic practical situations. So after studying this particular topic, student can understand the steady flow energy equation, and he can be able to apply this steady flow energy equation to deduce the various relations for the real mechanical systems. So, but before going to that one, what is meant by steady flow? So, the steady flow means the rate at which fluid flows through a machine or the piece of apparatus remains constant. So, this type of a flow is called the steady flow, right? So, the unsteady flow equation is also there, but that unsteady flow energy equation will be applicable for higher studies. So at the BTech level, this steady flow energy equation has to be studied. So before going to develop the expression, some certain assumptions which you have student has to make. So that is here the mass flow through the system remains constant. Mass flow through the system remains constant, and fluid is uniform in composition. The only interaction between the system and the surroundings are the heat and work, and the state of a fluid at any point remains constant with respect to the time. In the analysis, only the potential and kinetic energy flows are considered. So these are the assumptions before developing the expression. These are the points you have to write up. So this is the diagrammatic sketch, and in this diagrammatic sketch, if you just observe that and this is the mass flow rate at the inlet state condition. So this is the mass flow rate at the inlet state and the mass flow rate at the outlet state. So in this case, the kinetic energy term. So here the kinetic energy term at the inlet, potential energy term at the inlet, and the internal energy of the flow at the inlet, and the flow work at the inlet state plus or minus d bar q by. So here this is an inexact differential d bar q by dt is equal to at the outlet side the mass flow rate times into the kinetic energy, potential energy, internal energy, flow work, and plus or minus that is d bar w by dt, because this is also an inexact differential. So this is the expression of the steady flow energy equation. So once this equation is developed, then uh, the question which you can expect to derive the steady flow energy equation with assumption. Sometimes there are two inlets and two outlets in a system is going to happen. So when more than one fluid stream is involved, the basis of energy flow per unit time is more convenient. So the basis of energy flow per unit time. So the basis of energy flow per unit mass is there and per unit time is there. So in this case, whenever more than one fluid stream is involved, the basis of energy flow per unit time is considered. So this is energy flow per unit time is more convenient. So the mass balance. So this is at the inlet 1 and inlet 2 is equal to the outlet 3 plus 4. So this is the outlet. So this is nothing but the continuity equation. So what is nothing but the continuity equation? M dot is equal to A1 velocity of the fluid is V1 or C1 divided by the specific volume. So A1 is the area at the inlet. V1 is nothing but the velocity of the flow of the fluid divided by the specific volume of the fluid at the inlet. So in the same way, the energy balance equation can be represented like this one here. So that energy balance equation, which is consisting of the potential energy, kinetic energy, enthalpy terms, right? And the inexact differential, that is d bar q by dt and d bar w by dt. So this is d bar q by dt and this is d bar w by dt. So this is nothing but the steady flow energy equation for two inlets and two outlets. When you apply the steady flow energy equation, Then what are the expressions which are going to be getting? So deduce the steady flow energy equation to the nozzle, throttle valve, compressor, turbine, and heat exchanger. So this is the question mostly it is expected. So when you apply the steady flow energy equation for this nozzle, then what is the expression that yeah, you are going to be getting? So by applying this one here, because this is totally the insulated one, so here you can get that is H1. So so here you can get H1 plus V1 square by 2G is equal to H2 plus V2 square by 2G. So sometimes this velocity of the approach, so here velocity of the approach is 0, right? So in that case, the velocity V2 is equal to root of 2G into H2 minus H1, right? Or root of square root of 2 into H1 minus H2 that you are going to be getting, right? So that is V square by 2. So this is V square by 2, right? So yeah, like that one, the steady flow energy equation, if you apply the steady flow energy equation, the finally the velocity of the flow through the nozzle, it is equal to root of 2 into H1 minus H2. So this is how we are going to get the expressions like for all these cases. So the nozzle is nothing but which increases the kinetic energy of the flowing fluid. Diffuser is nothing but which it increases the pressure energy of the flowing fluid. So in the same way, there is a turbine is there and the compressor is there. So the turbine, which is when you apply the steady flow energy equation, then we can get the work output. So the turbine work output which you are going to be getting is H1 minus H2. H1 minus H2. So that is this is the positive work output you can get it. Whereas in case of a compressor, you need to spend the work input. So that work input is nothing but also equal to that is H1 minus H2, and this is a function of the temperature. So Cp into T1 minus T2. So this type of a equation which you are going to be getting in this particular site. So this is how the steady flow energy equation, and you can apply it for the steam condenser. Then after then you need to study the perpetual motion machine of the first kind and perpetual motion machine of the second kind. So perpetual motion machine of the first kind is nothing but it is a system which continuously produces the work output by taking or by extracting heat with a single reservoir. So that is the perpetual motion machine of first kind. But practically it is not possible. So that's why PMM1 is thus impossible. So the first law states that the general principle of conservation of energy. So energy can neither be created nor destroyed. So there can be no machine which would continuously supply the mechanical work without some other form of energy disappearing simultaneously. So here you need to give some work, some heat input to this one. Then only you can expect the work output. So what is the second law, that is perpetual motion machine of a second kind? So the perpetual motion machine of second kind is nothing but it is a machine which produces continuously work output by exchanging heat with a single reservoir. So that is also impossible. So these are the two statements which are connected to this particular unit, that is the perpetual motion machine of first kind and perpetual motion machine of second kind. So thank you one and all for listening this particular topic.